Steve Ellswick and the gang for producing another great conference, which we'll all benefit greatly, I think, and get a chance to find out some new things and talk about some old things. The presentation I'm going to do today has to do with static electricity, and I've been trying to figure out exactly how I'm going to do it. Some of the difficulties that occur here is trying to fit all this in a short amount of time or a reasonable amount of time and try to make a presentation that makes some sense, so we'll make every effort. And I think what we'll probably do is, due to the time factor and what I've been talking about, perhaps after this is finished, if there are any questions, I'll be out in the corridor so we can kind of catch up on the program, and I'll answer some questions out there. I regret that I have not been able to bring with me a lot of equipment to demonstrate, like my friend Bill that just gave the last presentation. That's a hard act to follow. But even if I had the opportunity, I still have to come about 1,600 miles, and so packing machinery and such like that is sometimes quite difficult. During the last 8 months, I have devoted most of my time to working with static electric generating machines, antique ones in particular. And I've been doing some restorations on the several pieces at Cornell University, as well as I have subsequent, or at the same time with that, I've also been working with developing some modern versions of some of those original machines. And so I thought it would kind of be good if I was able to make some presentations on that here at this get-together. One of the things I do want to do toward the end of this, if I have a few minutes, I would like to give you all some energy to experiment and build these things. And so I have a few references and a few ideas I want to put together. There's some excellent books in the bookstore, and so hopefully I can get you to do the one thing that is far beyond anything that I can say, which is to do a little experimentation. And believe me, that's quite interesting, quite amazing. Where to begin with this? Well, I'm not certain of what our predecessors in history experienced with static electrical experiments, or just plain petting the cat or rubbing one's hand over a fur garment and hearing some crackling, or things of that particular nature. And I'm certainly not certain of what experiments the Egyptians and people like them did with this. I doubt if they did a lot of experimenting, because at that particular latitude the climate does not really present a great situation for the working static electricity. However, I must relate a quick story. I did an electric show for a summer camp about 2 weeks ago, and when we got there with our equipment, it immediately rained, and the humidity went up to about 100% at least, and here we are standing there with all this equipment, and so I had to take my silk scarf and all of my plastic and glass rods that I used to induce charges into these static machines and take them, put them in. First of all, we put them in a convection oven, but when we turned it on, the fan in there sucked the scarf into the fan, and so I wound up with only half a scarf, but half a scarf is better than no scarf at all. And so I finally took the rest of the stuff and put it in a pizza oven that was kind of cooling down, and then we ran it from the pizza oven right into the display area, and I'm sure it was only with the help of the Almighty that it actually worked. But that is only because we were using induction machines, which we'll talk about here today, as opposed to frictional machines. Although I had to rub the rods with the silk, it managed to work. So Murphy isn't always present at a lot of things. Michael mentioned this book that Steve Ellswick has produced by Peter Peregrinus, which is concerning a good text on magnetism, very early one, about 1200. But that's a good point of departure for the information that I'd like to present here today. And no one is absolutely sure of the beginning of the first experiments with magnetism, although we have a lot of information from the Greeks and the Romans and other people with lodestone and the effect of actually attracting metal objects and so on to that lodestone. But I think that's the gang on 20 meters there or something. But aside from that, the idea of attraction also was produced by the Greeks, Thales himself in the 5th century BC, by rubbing amber with some pieces of fur and being able to attract bits of dust and paper. We know about those experiments. And However, for a long period of time, not any great scientific advancements were made. I'm not certain of the work that the Chinese were doing, and I'm not certain of the work of the Islamic cultures were doing during the period, say, from the time of the Romans up until the, say, the Northern Renaissance. However, it is obvious that some things were happening, but it's not easy to know. And of course, with the destruction of the great library at Alexandria in the 4th century A.D., destroying all the amazing papyri and texts that the Egyptians sent down to us, it's very difficult to know what kind of experiments had been done with this. Probably in the late 13th century, a gentleman by the name of Alexander Nechem actually brought the first compass device to the West, and it was they began to use this in navigation. And learning how to make this thing work and so on was interesting, but relatively simple. This object hanging from a string always pointed to the north, so therefore you could tell basically that that's where the north was, and so for a very limited amount of navigations and so on, that was, you could use that and everything would be all right. Well, when Columbus set out for the west, for the Indies, for India, or China, where he thought he was going to be going, among the many troubles that he had, and I suppose there were many, but his crew was really scared half to death because they believed, and traditionally, that you would sail out for a ways, and I guess the Viking stories is the wind would blow you to the poison sea, and then you would sail off the end of the earth into Hades, and that would be the end of you, and people believed that that was really going to happen. Well, at any rate, the very primitive navigation device and compass that he carried after they got sailing for a while, and of course they did have navigational charts that had come down from the Islamic cultures through the Spanish translators. I guess they were found at Jundi Shapur in Iran in the Crusade times. They were still around and brought to the West. They did have some navigational charts and so on, but one of the things that happened is that the compass at the time failed to point to what should have been the north. And I imagine that that particular situation, more than anything else, caused Columbus a lot of grief when his crew really didn't want to listen to him saying, sail on, sail on. Something had to be done about this, and Queen Elizabeth, Queen of England, England being a great nation, navigation, decided that it would be a good idea if some major experimenting would be done with magnetism and the compass, and try to understand why these needles, these iron magnetic needles, would be attracted to the north, and what in fact might create some problems for this, why it might not work. So what did she do? She got her own personal physician, a gentleman by the name of William Gilbert, and asked him if he would not embark on a great deal of experimentation and see if he could understand this idea of magnetism. Now, we need to understand at the time that people considered that attraction, things being attracted, whether you rubbed a piece of amber and you attracted some objects to it, or you had a magnet and you were able to attract metal, all that attraction was considered to be the same effect. And so in the beginning of Gilbert's experiments, he wanted to take a look at a wide range of procedures that would produce this effect. So he covered a lot to do with what we know as magnetism. And he also covered a lot of areas of what we would call static electric attraction through friction, by rubbing objects and so on. And he built some of his works on a gentleman by the name of Jerome Cardan, who had published some materials around 1550 dealing with all these different materials that you could actually get, and if you were to rub them, separate charges in them. He didn't know it to be that because it wasn't understood as that way, but you could cause this attraction to occur. So Gilbert, taking this work and his own work, and after about 16 years of experimentations, he published a work just about 1600 called All About the Magnet, called De Magnete. And it was, without a doubt, an instant success throughout Europe. And the book spread to many different areas, and a lot of people read this book and immediately began to experiment with a lot of the information that was given by Gilbert. Probably one of the earliest, and at least for the topic I want to talk about today, experimenters that did read this book and was totally taken over by it was Otto von Guericke. He was the mayor of Magdeburg. He is also very famous he is famous for a number of experiments. One of them is the famous horse experiment, where he took two hemispheres, put them together, pumped out a vacuum inside of them, and then had horses try to pull them apart, and it was not possible to do. And he did a lot of, in his new Magdeburg experiments, he wrote a great deal about this. He also, that was not popular at the time because the accepted church opinion was that there was no such thing as a vacuum, so you had to be careful what you said in those days. But at any rate, he did publish a book on this, and in the book he also talked about experiments that he had done with some of Gilbert's suggestions and work. And one of them was, having looked at the idea of attraction being created by friction, and what was going with that, he decided to construct himself a piece of material that would allow him to do some good experiments with this. So he got a great big glass vessel and filled it, and put a stick down through the middle of it, and filled it with sulfur, molten sulfur, and let it cool and dry. Then he broke the glass around the outside of it, and he had himself a sphere of sulfur, and it had an axle going through the center of it, which he was able to mount on various kinds of trunnions and fixtures and spin this. And he, pressing his hand up against it, he noticed that, and I obviously had done this in the wintertime and in a warmer and drier place, but he was able to create and feel this attraction and this very strange effect from this sulfur ball that he had made. As a result of this, he began to experiment with how the ball would attract pieces of dust and pieces of straw, and he began to formulate some ideas about why that worked. And presented that just at the end of the new Magdeburg experiments. If it had, I guess if it had been sort of interspersed through the middle of that, perhaps it wouldn't have been paid a lot of attention. But it was, fortunately. In fact, one of the last experiments that von Guericke did was he performed the spinning sulfur sphere experiment at night, and noticed that along with the crackling and the feeling of this fuzziness around the ball at nighttime, he actually saw the blue glow of what we know to be corona, generated by some considerable voltage potential developed by separating electrons from positive ions on the surface of this sphere. And we have the beginnings of the electrical science. Well, his book was also very popular, and that spread to quite a few places. And experimenters at the time, many of them were clerics, religious people, priests, people, teachers, and so on, had the opportunity to do a lot of experiments like this. But at the time, it was interesting to understand what this was, and Gilbert had talked about a lot of sides of this, and people were not certain of what was going on here, although they knew from at least the number of things that von Guericke had said that there was definitely a difference between magnetic attraction from lodestone and the attraction that was being created by this new electrical effect that was being generated from friction. To produce this experiment further and to continue with the work, you had a number of people in Britain who were part of the earliest experiments with electricity. And of course, here we are talking about this science, and we're not talking about what the Chinese did, and we're not talking about what, like I say, the Islamic cultures at the time were doing, really just talking about what our own Western culture is working with here. So pardon me for not having a greater amount of information to talk about this, but it would be good if I did. Probably the best name that comes down to us is Francis Hauksbee. If you look in different texts and if you look in catalogs or pictures in museums, you sometimes see various machines. In fact, I think I want to bring my slides up now if I can. Let's see if this is bright enough. I have a few. Go ahead. Uh-huh. This happened last year, no, the year before. Oh, there we go. These are just a couple of interesting photographs that we've made of electrical discharge from the surface, from a point on a static machine. Go ahead to the next slide. Yes. Can you see that? Oh, okay. Yes, could someone actually move the blackboard? Yeah, just pull it around so that we can do that. This is a very interesting one here, and I'll go through these quickly till I get to the things I want to see. This is an example of two similar charges coming off of points, and you can actually see the electric field and the lines of force created in the field. And if you saw Bill's talk before, he had some interesting pictures of drawings of this kind of thing. But here's the actual photograph of the actual corona discharges within that field. So you have like charges here repelling each other. That's a rather interesting photograph. Go on to the next one, please. And this is a picture actually of the top of the Great Pyramid, and can't see this too well in the light here, but this is a group of people actually experiencing corona discharges off the surface of their fingers and their heads and so on up at the top of the pyramid, which is some 480 feet, and so the E field up there would be considerable on a good dry day. So the Egyptians under these circumstances may very well had considerable experience with static electricity. Next, please. This is another plate from a book by Camille Flammarion. Yes, thank you. Which you can see that a person up on top of a mountain here is experiencing a corona discharge right at the top of his head. Actually, that takes some courage or perhaps some naivete to be able to do that, because the next thing might be a considerably larger bolt directly to that area. You know, they always tell you around here, if you're walking the mountains and you feel this thing occur, you want to kind of hit the dirt fast. Next slide, please. And here are a couple of other good photographs from Flammarion's book talking about the phenomenon of St. Elmo's fire. That is the corona discharge off the top of the church steeple. You know, it's a curious thing. Whenever thunderstorms would come by, it was traditional that people of before, I guess, Ben Franklin's time, thunderstorm was such a frightening experience, and it still is that they would have the bell ringer go down to the church and ring the bells. Hopefully that would perhaps scare away the thunderstorm, or maybe to announce to the people that it was obvious that there was a thunderstorm. But there was always a lot of open employment in the bell ringing area as a result of that. Next slide, please. And here's another shot of St. Elmo's fire again, which is the corona discharge, the spars of the ship, the pointed parts of the spars of the ship actually discharging the highly charged clouds up above them at sea. Next slide, please. Okay, and here's another, this is a plate from a book by Snow Harris, which is called The Protection of Her Majesty's Ships from Lightning Discharges. Next slide, please. Yes, another plate from the same book. The absolute fascination and fear of these electrical discharges. Next slide, please. This is a very curious one here from the Flammarion book, and I put this in here because this actually, when I showed this to Jim and Ken Coram, when we looked at this, Ken immediately said, you can, there it is right there, how you produce ball lightning. You know, you need some carbon from the chimney, you need some high voltage to produce some ozone and the heat, and there you have three pieces of ball lightning. This actually is from about 1870 in Paris, that particular picture. It's a very curious one. Put that in there so we can see that. Next slide, please. I get to the, yeah, that's just another discharge. Next slide. Okay, this is actually a wood block from Van Guericke's work. And this is the sulfur ball that he had built for himself. There's a larger version over there sitting in a fixture so that it can be spun and it can be touched and actually to produce the static electricity that was part of his experiments. Next slide. Okay, now I talked about the after Van Guericke's book and some work by Robert Hooke and Robert Boyle, two very good English scientist of the late 17th century. Finally, the instrument builder for the Royal Society, whose name was Francis Hawksby, he was not trained or educated. As a matter of fact, it's been said when you read, he had some 40 papers published in the Philosophical Transactions about working with static electricity. It was said that though he wasn't a good writer and he didn't know English as well as he could and not a polished person, he certainly made up for any of that existed in the machinery that he built. And this is an example of a machine in which he is spinning a bottle over there and using that, putting his hand up against that bottle and developing an electric discharge from that, which he can collect on. Actually, this one here is just to actually excite the bottle. Now, another thing, just talking about Hawksby quickly, one of the things that he did was he also had read very carefully Van Gurika's work on vacuum pumps. Van Gurika actually took the old traditional fire extinguisher, which was a big syringe and a plunger, and he reversed the foot valve in the bottom of it, so when you pulled it out, you could actually start to create a vacuum. And he himself experimented by pumping vacuums inside of the cylinders that he was revolving, and that work off of the discovery by Picard at the Paris Observatory in about 1674, which was when the mercury in his barometer was being shook around. He saw lights flashing inside the part where the mercury had actually created a vacuum in the top of the barometer tube. And the mercury actually rubbing on the walls of the glass tube had separated electrons, which in their movement toward recombination, there was enough of potential there to actually ionize the mercury vapor and the oxygen nitrogen in the tube. So this is one of Hawksby's experiments, using a static electric generating machine to generate the potential just to ionize the rarefied air inside the tube. Next slide, please. Here again, you can see another one of his machines, a large flywheel at the bottom which could be cranked, which would turn. What they used to do is they used to get old retorts. This was really popular, and they would simply break the big arm off the retort and use the top part of the retort and cut that off and try to drill through there and make yourself a sphere that you could rotate. That was popular at the time. Next, here's again concentric bottles that he had with different levels of vacuum inside them, in which he could observe various levels of the effect of the. Actually, some of these even had mercury inside them, and when they spun, they would light up and create all kinds of triboluminescent, that is frictional electricity, and excitation of rarefied gases, that is oxygen, nitrogen, and then obviously the mercury vapor that was left in the tube. Next slide, please. This is one of his mercury experiments. He would pump a vacuum out of this, and at the base of in the tray there was mercury, and when he would open up the valve, the mercury would be sucked up into the top of the tube, and it would fall down the sides of the tube and create this wonderful sort of 4th of July kind of flashes and scintillations inside the tube, which he called mercurial phosphorus, not understanding the actual thing that was occurring there, the excitation of the gas molecules in the tube. Next slide. Okay, now we'll let that sit there for a second. The Hawksby's evolution of the static machines, I know this looks kind of weird, and if you did this kind of stuff today, you'd probably get busted for child abuse or something, but this was a really popular thing in the early 18th century. And let me go back to where I was. Hawksby had published at least 37 or 38 papers in the Philosophical Transactions in the early part of the 18th century, talking about all of his static electrical experiments, not understanding really what was going on here, but understanding how to produce the experiment and how to make it work. And he also mapped out many, many pieces of equipment that you could build. So it was the rage all around Europe for people to experiment with this. And everybody was doing it. And early on in the 18th century, there were two people in particular that we want to talk about in quickly, as the time flies by, passing over this. The Stephen Gray and Charles Dufay both worked in the early to mid part of the 18th century, somewhere in the 1720s, 30s, and 40s. And these gentlemen were the first people to really approach this science, the studies of this, with some kind of scientific method. And Gray and Dufay both experimented with conducting electricity. And even Dufay himself actually coined didn't call it positive and negative electricity, but he coined the term vitreous electricity and resonance electricity, were terms that Dufay developed. And what he had done is he showing that they both had different effects, and there was effects of attraction and repulsion, and effects of how these two different kinds of electricity were working. Stephen Gray himself, as I say here, he was famous for this operation here, and what he did was he tried to show how electricity could be conducted over wires and other kinds of things, as well as if you were to suspend, and this is how he wrote it in his papers. He said if you were to suspend a young boy from silk thread, now this must have been pretty good silk thread, from the ceiling, and have his feet to be touching against a spinning glass sphere, and if you notice, someone has their hand against that sphere, I believe. I can't see that clearly, and you generate the charge, and then the charge is passed on to this boy, and then he's passing it on to this other young child over here, and she's holding up some kind of a thing above some pieces of paper or whatever, and that there's a conduction of electricity going on here. They actually were able to conduct electricity more than 12 or 1,300 feet in these experiments. And so these gentlemen finally ending up with a fellow by the name of William Watson, who was a doctor and spent a great deal of time taking all this work, putting it together, and beginning to, and we're going to talk about this a little more in a few minutes, use it for some kind of medical work. But at this point, we have to take a look at some very important, probably one of the most important discoveries of electrical science at the time, and that's the discovery of the capacitor. Now, it depends on what country you come from, who you're going to say really discovered this, but it is probably true that a gentleman by the name of Ewald von Kleist in mid to late 1745 did the first primitive experiment with what we would call the electrical capacitor, or at that time it got to be called the Leyden jar, because at almost the same time there was a gentleman in Leyden by the name of Peter von Muschenbroek who had, people said he was the discoverer of this, but he was the first scientist to actually sit down and formally and rigorously work with this. So there's a kind of a contest going on here between Ewald von Kleist, a German, Andreas Cuneus, and Peter von Muschenbroek, the two Hollanders, about who discovered the Leyden jar first. Could I have the next slide, please? That's just another rather large Hawksby-type machine. Go ahead, come, next slide. I want to try to get, here it is here. Well, this is basically what happened. As the story has it, von Kleist and his people, he was a cleric and in charge of a cathedral in Pomerania. They felt that this electricity, obviously, this wonderful discovery they had, must have had some tremendous power. And if you were able to use this medically somehow to improve your condition in life, it would be really great. Would there be a way to do this? Well, the alchemists talked about electric and magnetic fluids. Now, we may yet discover that there's something about this, but having believed this at the time, people like von Kleist decided that there might be a possibility of actually dissolving some of this electric fluid in water and then drinking it, thus improving all kinds of facets of your health and well-being, perhaps your luck and good fortune, whatever. So what he did was he got a bottle and simply put a nail in the top of the bottle. And actually didn't even use a nail the first time, so they say, but for the purposes of talking about the possibility, he put a wire or a nail in the top of this and held it up to a machine that was generating static electricity. And this is not the exact picture of the original discovery, but it shows it enough. And held it up there for a while, holding his hand to the outside of it. When he was finished, in order to pour the liquid out into a glass and consume it, he, while holding the jar, reached over to take out the nail and got the surprise of his life. Immediately, tried to reproduce the experiment. Actually, he told his friend Johann Winkler about this, another experimenter who actually had first suggested using amalgam-treated leather pads instead of your hand on these spinning spheres to improve the output of static machines. So he told Winkler about this, and he said, gee, look at what's happening here. This is, showed him the experiment, and Winkler said, gee, we've got to experiment with this. But Winkler was a well, I don't know even how you would describe him, but instead of him doing, he got his wife to do it. And so they had quite a few experiments and wrote some papers about this, of which his wife's name was not included. Typical, I suppose. But anyway, it didn't take long for this to get around, and as the story goes, von Muschenbroek, who was a natural philosopher and experimenter at the University of Leiden, did a lot of experiments with this jar, and it became called the Leyden jar because of his prominence as an experimenter and so on. He was given the credit with the discovery. But if you read his work and you see the way he went about his experiments, you would immediately realize that although he did manage to take a fairly good jolt of electricity, von Muschenbroek was a high-quality experimenter who knew experimental methods and would never have done what the description of the discovery was all about. And because had he done that, he would have wound up getting almost electrocuted like the other ones. They say he probably wouldn't have done this. So he, on the recommendation of other individuals, did these experiments and then, of course, published some papers and got the credit for it. Next slide, please. This is one of the earliest photographs I have of nice jars. I don't have. This is in my own collection. This is a jar from somewhere in from the 1880s, and this jar came from an early Betz induction static machine. This is a water Leyden jar. You put water inside as the inside plate, and as opposed to a foil. So this is like a very early form, although it's a 19th century piece. Next slide, please. And here's another one. This is a jar from a Tepler-Holtz Betz static machine from 1885 with an adjustable pier upon which the upper sphere sits. You can move it up and down and adjust that, and you can actually see the other connectors inside, which touch a tin plate on the inside of that glass as well as on the outside. Actually, this particular jar is a wonderful jar. It actually is about 1,100 picofarads that develops, and it puts out a tremendous spark when charged well. It's quite a fine. Can't find anything like that anymore, even to build something with. Next slide, please. This is Ben Franklin's own Hawksby type static machine, and we want to give a few seconds of discussion here to Mr. Franklin, which we should be able to talk about for hours. In 1743, Franklin was in Boston, and he saw an electric show by a Dr. Spence, who had a wagon full of all kinds of machinery. I sort of am partial to this because I have a car full of all kinds of silly electric machines, and I take it around and do this kind of stuff when I can. And Franklin, having seen this, and at that time having become a successful printer in Philadelphia, decided that he would see if he couldn't buy this equipment from Spence because he was completely taken by the experiments, which he did, and began his career of experimenting with electricity. Now, several things about Franklin. First of all, this is his Hawksby machine, which he actually got Peter Collinson, who was a brother of the Royal Society in London and a person who was a good friend of Franklin's, to have this made by, I believe it was Cuthbertson instrument makers in London, had it shipped over to Philadelphia. Also, Franklin had a number of other, we'll have a look at these kind of machines, shipped over to the Americas to give out to the various universities that were around at the time to experiment with electricity along with the work he was doing. This is your basic frictional static machine, and you can see that there is a leather pad at the bottom, which is treated with some kind of an amalgam that depending on what you wanted to use, that would allow you to separate electrons from it. And around the top you can see there are 4 fingers of copper wire sitting down and touching the glass, and that is what's known as the prime conductor. And you cannot see that around in back of the machine they have a ball, which is a small capacitance to pick up the charge so you can work with it. When I was a kid in Philadelphia, they actually used to run this machine at the Franklin Institute, but they don't do it anymore, unfortunately. Beautiful machine. Next slide, please. I think there's another slide of the same machine. Yes, this is the machine as it actually sits now in the Franklin Institute, and you can, behind it, see the capacitance, the ball that's behind it, enough capacity to be able to pick up this charge and hold it so you could do some experiments. Next slide, please. Okay, I think we're going to stop here for a second and talk about Franklin quickly. Franklin contributed a number of very important things to the understanding of static machines and the medical side of this. The first thing that he became aware of and talked about was, and understood from his experiments with Leyden jars, that in fact the Leyden jar was not something that you simply filled with, quote, electricity. And in fact, he described electricity as something that had a positive and a negative side to it. He said if it lacked electrons, he didn't use the word electron, but if it lacked some of this electricity and it had a positive charge, and if it had an abundance of this electricity, it would have a negative charge. So he gave us the beginning of this idea of positive and negative electricity with some real substance to it, because his experiments with these Leyden jars showed him that obviously one kind of electricity would stay on one side of it, another kind on the other side, and if you were able to bring the two together, you would get a discharge of electricity as these two wish to unite and become neutral or balanced, which is the truth of it. And so that particular idea was very important to us in understanding how to work these machines and how electricity went on. Also, the first Philadelphia experiment, and I believe tonight I heard Michael talking about there's going to be a seminar on the second Philadelphia experiment. But the first Philadelphia experiment took place in Philadelphia in about 1749 or 1750 or so, in which Franklin, considering the fact that what he saw up in the sky and what he saw coming from his Leyden jars and his static machines had a similar effect in the odor that they gave off, and then also in their appearance. He also, and this contribution is amazing, what Franklin did, a lot of people think Franklin went out and flew a kite that had a piece of wire that went up into the clouds and connected with a thundercloud and came down, and he was able to charge a Leyden jar with it. Well, let me tell you, if that were true, you know, Franklin would have been a piece of toast at best in 1750, and there wouldn't have been any other developments from this. It really wasn't the case. What he did was he actually was outstanding in what they call a sentry box, so he could keep out of the rain, because he was smart enough to know that he didn't want to get wet and become very conductive, and his kite string was going up in the vicinity of the storm, and when it came down to the ground, he had a piece of silk tied onto the bottom of the string, which he held, actually, a silk ribbon, to keep himself insulated away from this, and a key was tied onto the string, which he held near a Leyden jar, which was earthed or grounded. And what happened is the string got wet. It became a little more conductive, considering the potential of the lightning storm and so on. He was able to conduct electricity down, charge his Leyden jar, and produce the very same effect that he was able to produce with a static machine, except the charge was considerably more, and it was very quickly obtained. As a result of this, many other people decided that, considering that static electric machines are hardly ever work at the same time that you have a lot of thunderstorms and rain, so therefore you couldn't do experiments in the summer, and as a result of this there had to be another method found to do it. So people began to improve on Franklin's ideas, also on his ideas of how lightning rods work. And to make a long story short, it was very popular to go up on the roof of your house, and if you were well endowed financially, had a big house, you go up on the top and put a very long rod up above your chimney and bring that down either into your house, or you could be up on the roof and simply use that as a way of discharging thunderclouds and so on, and being able to get some of this electric virtue and charge up your Leyden jars so that you could take them to your laboratory and do various experiments with them. Needless to say, Franklin was extremely lucky, and as odds would have it, this method of gathering electricity was popular for a while, but next slide please, as we will see along here, was not extremely successful for a lot of people. I have a series of slides here, so I'm going to move along quite quickly with this, just showing some of the finer quality frictional Hawksby type static machines. And this is the very standard type here. You have the glass drum with wooden trunnions and up on a stand, and then there's in the back here there is a piece of spring metal which presses a piece of leather or other treated in certain ways material against the glass so that you can crank it around and bring electrons around to the other side and collect them onto, or positive ions, depending on how the charge is running in this case, to the other side and collect it. You can't see the prime conductor on this, and if you look here, this also has not only a pressure pad, but there's a piece of material running over the top of the glass to add a larger surface area of friction to separate greater charges. Next slide, please. Again, this is the same type of machine with a very old style Leyden jar down here, which does not have, it has a ball on it, but it's a hook, so you can hook it on and to the prime conductor of the machine. Next slide. I want to move quickly through these. Let's see. Again, this is a whole system which, let's see, this particular one belonged to John Wesley, the founder of Methodism, and one of the ways he himself, I think, imparted some of his religious teachings with some electrical fortitude in the background to add and increase the effect of God's energy, which I no doubt there's truth to this. Next slide, please. And we see just various kinds of machines here in various museums around the world. This again has a larger flywheel for cranking the frictional disc around to generate the charge. Next slide, please. Yeah. This is a good example. I talked about the prime conductor. As more was understood about charges and how they would leak off and how you wanted to store them with some kind of capacitance so that you would have a better opportunity to take charges off these machines, this object here with the balls on the end and the round, smooth, highly polished, this was referred to as the prime conductor, and on the other side of it there were some fingers of wire or something sticking out which would actually enable a corona discharge coming off the spinning glass and be able to charge up that body of capacitance there and hold that charge for different experiments that they wanted to do. Next slide, please. Again, another different development of machine. Next slide, please. There's a grounded discharge stand or an elevated capacity over there to experiment with something called static electrical induction, which we have to talk about here in a minute. But that's what that particular one is. Next slide, please. Next slide. As you can see, there's a very basic setup here. These are all 18th century machines, some perhaps early 19th century, mostly 18th century machines. I myself went to the Antique Wireless Association flea market about 5 years ago, and underneath a truck I saw this box with a glass vessel in it, and I said, I think this is my lucky day, because what was in the box sitting under the truck was the trunnions, the glass drum, and the crank handle to one of these early machines like this. And I cannot know this for sure, but Franklin ordered 10 of these from Cuthbertson and Company and gave them to Yale and Harvard and other universities to do experiments with. I'd like to think that there might be a possibility that the one that I have, which is exactly like this is the exact machine that was the standard one that Franklin ordered. It'd be nice if it was one of those. I don't know. Next slide, please. Next slide. We'll just go through these. These are just your basic. Okay, now this is just another level of evolution as the effect and methods of working these machines was improved upon. And what you have here is now we have glass discs that are spun around. On the top here there is a amalgam coated pad which and over here there's a drape going over the edge of this which rubs, probably made of silk, which rubs against this, and the charge, you can see there's another one over here as well, and the charge being collected on these collectors on either side and stored in these capacitors here and discharged over out of this. This was the machines that were developed in the latter part of the 18th century. A lot of this for medical use because these were much more efficient machines and much easier to operate. And their configuration was much better. Next slide, please. There's another one. You can see the same effect with the capacitor sitting down here. Next slide. Next slide, please. These are actual museum pieces. You can see the way they're done. Up top is where up in the top and the bottom part right here you can see the pads, the frictional rub. Where am I here? There we go. Here, and this is the pickup brushes over here, and you just simply crank that, and so on. And there's a little clapper experimental piece which we won't get to talk about right here, where when this little gong clapper comes over here and picks up the same charge as on the bell, it's repelled away, and then it induces the opposite charge, and it's attracted, and so it sits here, and it's kind of your first doorbell, and kind of sits there and goes ding, ding, ding like this. I know that sounds kind of simplistic, but in those days it was an amazing effect to see kind of a motor at work with that. Next slide, please. And here's a really complicated one. It has a much more 4 pickup brushes, so you can pick up more energy to feed into that capacitor. Next charge. Next slide. Very nice art pieces. Next slide. Next slide, please. Quite a nice sized Leyden jar there with a good capacitive termination on the top. Next slide. Next slide. And they keep getting bigger and bigger as time goes on, and improvements made for greater sparks. In the background you can see a bank of Leyden jars there for larger energy discharge and so on. Next slide. Now this is the probably the last and most famous of the generation of frictional static machines. This belonged to Martinus van Marum, and it was built for him in 1790 by John Cuthbertson of London. It had 2 6-foot spheres of glass mounted, and it had in the back, you can't see the whole machine laid out. This is at the Tyler Museum, and Van Marum actually was one of its directors back at that time. But this machine, when properly set up and working with its capacitors set up, you can see all these different elevated and isolated capacities around. And in fact, flip the slide and see if I have another picture of that. That's his bank of Leyden jars. There's 100 jars in there set up so they could be charged. One more slide if we can see this again. No, come back to. I thought I had another picture of that. No, go back a couple of slides. One more. Go back again. Go back again. Okay. This machine, when working properly, could hurl over a 2-foot bolt of lightning that was extremely loud and extremely lethal if you were actually and with that bank of jars, in fact, that we showed here, I believe that this machine, 200 joules, I think the figure that I just heard quoted was able to produce 200 joules of energy stored in those capacitors in 1790. So we're talking about some interesting amount of energy there. Next slide. And that's the bank of jars that he had. Okay, now this, how are we doing time-wise? Well, we're just about out of time. It's typical. I want to quickly talk about the induction static machine, because just quickly to discuss how it works. It was discovered as early as 1753, the idea of electrostatic induction. Essentially, if you take a sphere, an uncharged sphere, neutral sphere, or a sphere with could have some charges on it. If you move it close to a charged object, you're going to get an induced charge in the sphere. That's very basic physics. And the idea of this in the experiments by John Canton around the 1750s, he had experimented with this and realized that you could actually charge things by induction at a distance. Alessandro Volta, I believe, is the inventor of the electrophorus, and that is a machine in which you can induce a charge in a metal plate. And what they usually did is it's a bound charge, because you have if you have a positive charge on your plate, you put this piece of metal close to it, you're going to get a negative charge induced on the base of it, which will cause other positive charges remaining in that thing to be repelled to the other side. If you quickly ground the other side, you can use your finger, that's what they used to use, then you can pick that thing up and have a free negative charge on this, which you can actually put someplace and use it. So this is the electrophorus, and this actually, a gentleman by the name of Abraham Bennett, as like it took, what, 30, 40 years for this to be worked out. He's the inventor of the gold leaf electroscope. But he had actually constructed a doubler in which he was able to keep taking these charges, making them free, and keep storing them over in another area, and kept building his charge up, just like taking a teaspoonful of water and so on, and keep putting it so you get more and more and more water in a container. This developed a new idea, and this one right here I have up here because I can most simply display this to you, if I can move over to the blackboard here, how this new idea works. This is rather curious. And I'm running out of time, unfortunately. I have about a ton of things to say, but let's see if we can you see this? Let me just quickly describe this to you. Let's just say if you had two cans, and you had a positive charge here and a negative charge here, and you had a piece of glass with a, let's say you have a ball on the front of it here. If you bring this ball over close to this positive charge here is going to induce some negative charges on the surface of this, which will repel if there's any other positive charge over the edge here. If you were to ground this or touch this, then you would convert this bound charges here into a free negative charge. If you take this over, this is not positive, it's negative. If you were to take this over and put it inside of this container, using some of Faraday's laws, you would understand that that charge would appear on the surface of this container, so you would have some negative charges here. If you were to then take this, ground it, neutralize it, and come back over here and do the same thing, you could get the same effect to take place, and you'd have the opposite charge, some positive charges, go over and put it inside of here, that the work you might do with your hand on this, the work that you're doing with this, would increase the charges continuously in here as long as you could sit here and go back and forth with this process. Well, what happened is that Varley and Tepler and Holtz and eventually James Wimshurst, who put together probably the most successful of these machines, realized that perhaps they could do this with a little more efficiency. So we look at this machine up here now. This is a Tepler machine. This is actually a late 19th, early 20th century version of one that we see here. But essentially what they did is they got a big brass plate, or it could be a disc, it didn't matter, and then they got a circular disc in here like this. God love people who can just visualize these things and pull this off. And over here they put a piece of paper, this underneath the glass, this part back here, with some aluminum on it, like so. And they did the same thing over here. This is on the opposite side of the glass here, insulated. And put a piece of tin foil on the other side of that, real tin that is at this time. And then they take a brush that comes out connected to this tin, and they bring it out, and they bring it over here, and they do this. Why did he do this? I got it backwards. Let's do it this way. It comes out like this with a brush. Okay, let's get this one off here. And up here they do the same thing. They come over the top and put a brush down here. Then they get some little tin collectors, sectors, and put them around the edge of this disc. And this disc is able to spin, and you have a crank over there where you can get this disc to spin. So let's just say the disc is spinning this way. So what happens? Well, we know that there's always some charges laying around, from cosmic rays and other things that are always going to be present on these things, or you can actually, with some frictional method, you can induce some charges on these. Also, they have little surfaces on these things, as you can see. All it is just to hit it with a ball-peen hammer, so there's a little surface that can touch this brush. So what happens is when you start to spin this disc, any charges, free charges that are on these sectors over here, when they go by, they are going to, some of them are going to be picked up on this brush here and communicated to this piece of tin foil back here, which is going to become electrified. And let's make this the negative side of the machine. And then comes the most ingenious part of this. You take what's called a neutralizing brush, and you put it up here so that a brush comes down from this and down from this, which also will touch these little raised areas on these things. As this spins around and comes by here, gives this a negative charge, this is going to be positive. What happens is when these disks, which have given up their charge to this, pass by here, they have a positive charge induced on the bottom of them and repelling some negative charges up to the other side of this thing. When this, just at the edge of this inductor back here, this brush touches this, and the same thing happens down here with the opposite charge, so that the two charges actually neutralize each other, so that essentially without grounding, without like touching your finger to the electrophorus, it actually creates a free positive charge on these things which rotate around and go over here and do the same thing. So what you've got, and then you can put some kind of collecting, you can see where these collecting brushes are right on the edge here. You can put some kind of collecting brush that will touch these things and pull the charges off so that you can take them to some kind of discharge spheres and have an actual circulating system that spins around and by inducing charges back and forth can build up. Every time this happens, every time that you add charges to this, the inductors here get larger, so they induce a larger charge onto these carriers, and as the charge is larger, it increases the charge over here, which increases the charge over here, so after this machine spins, it builds up an enormous charge, and the only limitation of a machine like this is its leakage. In other words, these accumulators, sectors leak, or whether you have good terminations on your collecting brushes, they leak, and other parts of this. This is a marvelous visualization of how to build up electricity. It's, we can discuss this afterwards because we're definitely out of time. Thank you, I know. Let me just make a couple of quick recommendations here, and I'll talk some more outside so we don't get in anybody else's way. Building and experimenting with these machines is something that is inexpensive and is absolutely filled with, I mean, you can find out more stuff by doing this. I recommend to you, first of all, for those of you interested in experimenting and for those of you that wonder about where to get things, right here is the advertisement for something called Rolock food containers. Polystyrene, high Q, sealed at the bottom. It's one piece. They make the finest Leyden jars that you can build. Rolock, they're the only ones. I've looked, you know, far and away, high and low for these things. This is the best one. 200 kilovolt Leyden jars guaranteed, and they're cheap. That's one of the things I recommend for experimenters. You can find these at good quality supply stores. The other thing is, here is a book right here that I want to recommend to you. This is called Homemade Lightning. It's by R.A. Ford. My hat goes off to Mr. Ford. There's a lot of funky parts to what he's got in here, but there's also some genius involved in what he did. And he also was able to really do some experiments with some of Carl Winter's work and other people who were able to produce really good insulation, which is very important to make these machines work really well. This is a book that historically, technically, and so on, is just, it's worth, I think it's $14.95 or something. It's really worth it. Steve's got some great books over in the bookstore that also go along with this, but I highly recommend this book. I'm out of time. I have a lot to say, but that's it. Thank you very much.
Thank you very much, Jim. Yeah, it's one of those things, you know, there's some speakers